Right, in the next section, we are going to see data address space. So far, what we have seen is AVR's architecture and how the CPU is working with GPRs to perform simple functions like LDI and some arithmetic operations like add, subtract, and increment. Now, data address space is quite important because in AVR microcontrollers, there are two kinds of memory space. The code memory space, which we call it program ROM, and also the data memory space, where we have got GPRs and the RAM. So in general, data memory is composed of three main parts: the GPRs, the I/O memories, and internal data SRAM. As you can see, the address and their range over here, this is specific to Atmega 128 family. If you are having a different Atmega family, you might have different data address spaces with different ranges. But we are going to focus on AVR, so let's investigate that in detail. So we already seen GPRs, which is 32 registers starting from address 000 to 1F, which is 32 addresses. And then we have got 64 I/O registers. So what are those I/O registers? They're actually known as special function registers, SFR, where we have got the status register, where we have got the flags, where we have got the timers, serial communication registers, I/O ports. So in order to configure these functionalities on your AVR, we have to configure those registers. I'll show you in a minute those register table. And in some of the AVR families, we also have extended I/O register, another 160 of those, which we have more functions in there, depending on the family you have got. And internal SRAM, it's used for storing data and parameters by AVR programmers or the compilers. Okay, so we can use that part as a scratchpad, what we call it. Now, one important thing about the I/O register that I already mentioned, the function of each I/O memory is fixed. Okay, so you cannot change it. Now, that is fixed by the CPU designer, so the AVR designers, and they when they are designing it, they fix the addresses for it. And because they are used to control microcontroller peripherals and other ports, we cannot change those. So here are the I/O registers table. There, as you can see, we have got like port C, pin C, UCSRA, ADCSRA, which we are going to see AD-MUX related with the analog to digital conversion, UBRR for serial port programming, and pin B, DDRB, port B, pin A's, EEPROM addresses, status register, SPI, SPLH, SPLL, SPH, SPL. So these are all special functions that we are going to see in AVR, and they have got their own registers in I/O registers. Now, one thing that you might be asking over here is, why do we have two addresses? Like you have got I/O address and you have got memory address. Now we are going to see that now in details. Why is that so? So I/O memories and memories, I/O address and the memory address, we are having a separate instruction for those. Okay, and that's why we have got separate addresses for those, which I'm going to explain in a minute. So this is the I/O registers. Now, one thing that I want to mention before we get into these I/O registers This internal data SRAM, which we are generally using for storing the data and parameters, each location of this SRAM can be accessed directly by its address. So you can just specify the address 0x153, for example, and you can access it. And we will use these locations to store data brought into the CPU via input-output ports or in the serial ports. And each location, again, it's 8-bit wide and can be used to store any data we want as long as it is an 8-bit data. And as I already mentioned, size of this SRAM is also can be changeable, vary because of the chip and the type of the AVR that we are using. So you might ask, what is the difference between the RAM and the EEPROM that we have got over here? So you probably, as we already mentioned in the first lecture, you know the difference between RAM and ROM. One of them is permanent, other one is temporary. But EEPROM is used for storing data as well, and it doesn't lose its data when the power is off, where SRAM is that. So we are using SRAM for regular operations, but if you want to keep the data, we have to store it into the EEPROM, and we'll see how we are going to do that. And if you don't want to lose data, we store it over there. Okay, so once we understand the differences between the memories or the data address space, now we can easily start with the instructions of the data address space. Now, the first instruction that we are going to see is LDS. So what is LDS? LDS is, it tells the CPU to load, or we can say copy, 1 byte from an address in the data memory to the GPR. So LDS is doing data memory to GPR. Okay, so we are loading data from data memory into GPR in order to perform some arithmetic operation, for example. And the instruction is LDS RD, and I'll say address. Okay, so what does that mean? Address of the data memory will be copied into the GPR, where we are actually copying the contents of it. Okay, so the comment can be something like this: RD is equals ADDR. So ADDR is between 0000, okay, to anywhere in FFF. Okay, so down over here. So from any part of the data space, okay, starting from 000 to FF, we can copy it into a specific GPR. So RD is GPR, and address is between 000 to FFFF, 4Fs. Okay, so let's give an example and let's see how this is working. LDS R5 0 hex 200. So this is any address from the data memory, which is 200. So we are saying that this means load R5 with the contents of 0 hex 200, which is located in internal SRAM. Okay, so we are actually loading the value from hex 200 into R5. It can be any GPR, it can be any part of the data memory. Okay. We also have another example, which I believe it's good to try. The following program adds the contents of location hex 300 to location hex 302. Now, we have got two addresses which are part of the internal SRAM. Okay, and we are going to get the contents of these two addresses and add them together. Now, in order to perform the add operation, we have to put them into the GPR first. So I want to draw, maybe if I can fit it, data address space over here. So R0, R1, R2 goes to R31. And then we have got IO reg and some space. And let's say we have got 300 address, 300. Doesn't let me to do the dollar sign. Then 301. And 302, let's say. Okay. So we have to get the contents. Let's say I have got content as in 300 as alpha and 302 as beta. Right, so what we need to do is I have to get these contents from here to somewhere in GPR. Let's put it in R0 and R1. Okay. We have to put it over there, and then we need to perform the operation. So if we write the code for it, we can say LDS R0, it's going to be 0 hex 300. So we get the contents, which is alpha, into R0. And then LDS R1, and we had to get 0 hex 301, oh sorry, 302 values. And now we have got R0 and R1 has got the values. I can just say add R0 R1. So we add the contents of R1 into R0. So if you want, we can also show how this is looking like in the memory. We have got, let's say, instruction, R0 register, R1 register, location 300, and location 302. I couldn't fit it over there again. Okay, that's 302. Now, before LDS, we don't have anything in there. And 300 has got alpha, and 302 has got beta. Then after LDS, the first LDS, let's say, what we have got in R0 is alpha, and we don't have anything in R1. And also, this is alpha, this is beta. After the second LDS, now we have got alpha and beta in both of these registers, and alpha and beta over here. And add, after the third instruction, add, now we have got the result in R0, so that means R0 is going to be alpha plus beta, and R1, it's still beta. Okay, so this is how it is running with LDS instruction. And similar to LDS, we also have another instruction. So in this one, we have got data to memory. Now we have got STS, which is from GPR to data memory, store. Okay, this is a store instruction where we get the GPR value and store it somewhere in the scratch pad or data memory, any part of the data memory. So the instruction is STS. Now we have got the address and we know the destination, which is the GPR. Again, address anywhere between 0000 to FFF, and RD can be any GPR from R0 to R31. So if we give an example, we can say STS 0 hex let's say 100, and that will be stored so from GPR R15. Okay, so that means as a comment, let's say 0 hex 100 will have the value of R15, location of the memory, and of course the address. So this can be summarized in these slides, LDS and STS, with an example showing how this can be used as an instruction to tell the CPU what to do. Which means store direct to data space, which tells the CPU to store or copy the contents of the GPR to an address location in the data memory space. Okay, so we can do an example. Write a program and load register R16 with value X55. So I'm not going to write whole questions, so we can just read and write especially important things. So we have to load the register R16 with hex 55. So R16 will have the value 0 hex 55. Then move this value around to I/O registers of ports B, C, and D. So move value to port C, port D, port B, sorry, port C, and port D. Now, what are those? You can check it from here. The addresses. Port B is X38. Port C is X35. And port D is X32. Okay, I'm using the memory addresses. I will come to I/O addresses later on. I'm using memory addresses, special function registers that we have got. So that means each of these locations will have this value. That is what is asking to us. Okay, so we'll start with LDI. We have to first initialize this constant to R16, and we can say this is 0 hex 55. Then, as this is in GPR, I have to use STS instruction to copy it into the 3 different addresses. STS, I have to specify the address 0 hex 38, and that's going to be R16. And then repeat that, STS 0 hex 35, then also it's R16. And the last one, STS 0 hex 32, and that will be also coming from R16. Now each of these now, based on these instructions, 0 hex 38 has got the value 0 hex 55. 0 hex 35 has got 0 hex 55. And 0 hex 32 has got 0 hex 55. Now all of these ports, port B, port C, port D, will have the same value. You can do something else. You can store it to somewhere else if you want, and that's also a valid operation. So write a program that stores 55 into location hex 120 of RAM. So first we initialize 55 as a decimal into R20, then we use STS instruction and copy R20 into hex 120 in the SRAM. And we can use both of those together. Write a program that copies the contents of hex 20 of RAM into location hex 21, 121. So first, we can do is we can load the data from 120 into R20, any GPR, and then from R20 to any part of the RAM. So we can change the location, or we can copy the content into another data address space. Okay? Any part of the RAM, we can do these operations. So one another example, add contents of location hex 30 to contents of hex 35 and store the result in location hex 313. Now, again, we have to use both of these instructions together. First, we have to get the contents of hex 30, hex 130 to hex 135 into the GPRs so that we can do some arithmetic operation. Then we perform the arithmetic operation and we have the result in R20. Then we store the R20 value into 313 hex. Okay, so we stored in a different place in the data memory. Okay. What does the following instruction do? It says LDS R22. This is actually the GPR R2. Okay, so it copies the contents of R2 into R20, as 2 is the address of R2. Okay, be careful, this is not LDI, it's LDS. The contents of R2 is copied into R20. Another one, store hex 53 into SPH register. The address of SPH register is hex 5E. So SPH register is over here, hex 5E. So we need to initialize 53 first with LDI, any register GPR 16 to 31. We have used R20. So R20 has got 53 value. And then by STS, I'm storing this value into 5E, which is the SPH register. Okay, now these are, so what we have seen so far: LDI, add, subtract, increment, decrement, LDS, and STS. Another instruction that we can use is the in instruction. Now, in instruction, it tells the CPU to load 1 byte from an I/O register. So we can only load from I/O register, not from complete data space. It loads from I/O register into the GPR. Okay, I/O reg to GPR, and the instruction is in RD, and I can say A for this, because that should be the I/O memory. Now, RD is GPR, and this one, A, is I/O memory, which is between 0 and 63. Okay, 64 I/O registers is between 0 and 63. So for example, we can say in R20, we'll have the value 0 hex 16. So what is this actually? Now, this is the point that I want to mention. Hex 16 It's actually, when you look at the I/O side, it's pin B. So if you are using in instruction, we have to look at the I/O addresses because this is just specifying the I/O registers. But if you are using LDS and SDS, which we are looking for the complete data space, we have to look at the memory addresses. As we are using in hex 16, we can say that R20 will be equals to pin B. Okay, so we are getting the value of pin B copied into R20. That's what this instruction is telling. Also, we have got similar instruction, as you might guess, out. Now, out instructions tell the CPU to store the GPR into the I/O register. So we can say GPR into I/O. Okay, so other opposite way of in instruction. Now, let's say out, and this is going to be A, and that's going to be RD. Okay, so out, A, RD. Again, A is between 0 and 63, and RD is any GPR. And if we do an example, we can have LDI R20, let's say, will have the value 0 hex E6, and then I can use out instruction, out, and the IO memory, let's say SPL, and that will be R20. So R20 value will be copied into SPL register. So I can say that SPL equals R20. One important thing, we cannot copy an immediate value to IO register. Okay, so you cannot just say in R20 X16. So this is actually should be a address of the register. It cannot be a constant. So you cannot say in R16 5. That's not possible. Or LDS R16 5. Okay, so we cannot use that LDS, STS, and in instructions with the constant or immediate value. What we can do is we can use GPRs. We can get the value, store it in GPR, and copy it to another IO memory or somewhere else. So in, as you can see, .3f, so .3f is sreg, as you can see from here. So that means R1 will be equal to the value of sreg, and 3e is sph, so R17 will be equals to sph. And also the out instruction is similar. Then we get the value of GPR and copy it into the IO registers. So R12 will be copied into 3F, which is sreg. So sreg has a new value as R12's value. And R15 is copied into SPH. And we can have these all together. So if you want, rather than using these memory addresses, IO memory addresses, we can just directly use these names because these are all defined in the include file of the 128. So you can just say R12 to SPH, okay? So these are all defined. SPH is in address X3E, 3E, and SREG is 3F. You can just use those names next to it. Okay, so you don't need to take care of the address. You can just use the name directly if you know the name. Okay, another example. Write a program that adds the contents of pin C, IO register to the contents of pin D, and store the result in location hex hundreds. So what we need to do over here, we have to get the contents of the pin C. How are we going to get the contents of the pin C? We have to use in instruction. We have to get the contents to somewhere in the GPR. So let's say R20. From where? From pin C. Okay. And then we need to have contents of pin D. So in R21, pin D. Now we have got the contents in GPR, then I can do an addition operation. Add, I can add it to R20 again. R20, R21. So I add it over there. And then, as I have got the results in R20, I can store it in SRAM hex 100. I just need to use STS instruction over here, specify the address of the SRAM, which is hex 100 is given us. And then what value? I have to store the value of R20 over there. Okay, so this is how I can get the contents of two ports, pin C and pin D, into GPRs, and then perform the operation and store the result in any part of the SRAM.